Now I'm at Tableau Research just very recently, this past month, so sorry for those. Oh. Yeah. So sorry for those who are expecting a talk from Facebook. So my talk is on data sketching, on optimal cardinality estimation when you take data sketches and you take unions and intersections of them. So the basic problem for approximate distinct counting is that you want to count, say, a bunch of user IDs in some data, and you want to apply some filters, and you want to apply some group wise. And so the challenges of this problem are that if you're, say, Facebook, Google, any of these large web companies, you have millions or potentially billions of users. And when you do these group bys, you can potentially get millions of things you want to count. And this translates to using lots and lots of space. And the second challenge is essentially that you want to sometimes take these results and then give them back in a real-time fashion. So you want to provide real-time analytics. And these are partially already solved by using data sketches. And what data sketches are, they're essentially these memory-efficient summarizations of big data, typically to answer particular questions. So in this case, it's the approximate distinct counting question. And you're allowed to give approximate answers. And that's why you can get large space savings. So their applications are pretty wide range. You can have these online analytical processing systems, which I just described, counting the number of distinct users that see a web page. It can be used in networking to, say, detect worms by keeping track of unique IP flows. You can, say, use it in search, and also in databases and query optimization to estimate join size. So what are the existing works? So currently, the main algorithm being used in industry right now is hyperlog-log, and this is basically because it's the most space efficient. But it has, say, non-optimal union operations for merging, no real intersection operation. You have MinCount bottom case sketches. This is the one which I'm going to talk the most about today since the algorithms are derived for this particular sketch. And they have an intersection operation, but it's not really optimal. There's also some work on sort of the optimality of methods. There's Keynes' optimal method, which is similar to hyperlog-log, and they prove that it has optimal space complexity, but in practice, no one uses it because the constant for this rate is poor. We also have the streaming or historic inverse probability estimators that were introduced by Cohen and myself in 2 separate papers. And this estimator is optimal with an optimal constant. And it reduces the space for MinCount by a factor of two times, by 1.57 for hyperlog-log. But the problem with this is that it can't be used in a distributed setting, and that also causes problems in cases where you need to merge and to show reports or the OLAP setting. So why did I say this problem is only partially solved by sketches? So the problem, we can look at one concrete example. So say we want to look at the number of distinct users and from a particular demographic group that saw a page, and say I have just 1,000 pages. I have information about the country users are from, a little bit about the age, and the gender. And so if I just have this kind of problem, then I get 2 million counters. And with hyperlog-log, if I want 1% error, then I probably get a sketch around 8 kilobytes. And this already translates to using 16 gigabytes. Now, suppose I want to add a time dimension. I want to tell people the number of people that saw a page in the last day, the last week, so on and so forth. Then if I break this down by day, then suddenly I'm using 5.8 terabytes, or using 700 plus million sketches. So even though I reduce the sketch size, I still have this problem because I have this sort of exponential explosion in the number of counters. Right, so what are the possible solutions? There are two main possible solutions that you can sort of attack. One, which is that you want to reduce the sketch size by increasing the accuracy. And the other is to try to use fewer sketches. And hopefully, you can answer all the questions you can answer before. And one way to do this is by providing good intersection estimators. And the way you can see that this helps is that if I could estimate intersections perfectly, then the number of sketches is additive rather than multiplicative. So in that case that I just showed, then I'm going to use less than 2,000 sketches versus 700 million sketches. So the problem of intersection estimation is not well studied, which is what we try to address today. So what are our contributions in this paper? So our contributions are, first, that we actually give practical, easy to implement algorithms that actually give practical improvements in accuracy. So for pairwise unions, we do 2 to 4 times better. If you're taking the union of many sets, so this is kind of the distributed case, then you can do up to 2 times the number of sketches better. And then for pairwise intersections, you can do often 10 times better. Another nice property is that when we apply this to MinCount, it creates closed intersection operations. And so you can sort of compose these sketches further. And these have sort of broad applicability. So even though I derive everything from MinCount, you can apply the methods to other sketches, at least one of the methods easily to other sketches. And so we also talk about the theoretical results and how we improve the understanding of these distinct counting sketches. So although we don't give a real theoretical proof, we derive a heuristic approximation to a method which is optimal, truly optimal. And then we sort of point out the pieces of information which are not used in current methods, so the inefficiencies. So the outline of our talk is going to be, first, we're going to take this problem, we're going to establish it as a statistical estimation problem. This will allow us to sort of talk about optimality. We're going to identify the inefficiencies in existing methods, and then we're going to look at the methods themselves. So one method is the pseudo-likelihood method, which is just applying statistical machinery. And then the second one is the method which I would suggest people use because it's much easier to implement. And then we'll look at empirical results. So for our distinct counting problems, they're essentially all in this probabilistic counting family. And what probabilistic counting does is you take your problem, you transform it into a probabilistic process, and at the end of the day, you estimate a parameter from the resulting random quantity. So for approximate distinct counting, you have a bunch of data x, and then for every data x, I hash it to essentially a uniform random variable. I update my sketch with the constraint that the sketch is not going to be modified if that random variable has been encountered before. And so what you see is that when I do this, my sketch is going to be simply a function of the number of distinct, or n uniform random variables, where n is the number of distinct elements. And so it has some distribution governed by this single parameter n. I want to estimate this parameter n. So we can see this applied to the MinCount sketch. It's also known as bottom k, k-minimum values, min hash. So in this one, you simply take the hash values, you keep the k smallest ones. The k smallest one is the threshold. And you note that if it's hashed to values between 0 and 1, the threshold is going to be approximately k over n. So if I just take 1 over the threshold, divide by 1 over the threshold times k, I'm going to get something approximately right. And you can actually get that an optimal estimate is k minus 1 divided by the threshold. So in this particular case, it estimated 103. And my actual value over here is 100 distinct values. OK. So why does this optimal estimate not work well in terms when we come to unions and intersections and so on? So the problem with unions is that this sketch, when we take this merging operation, it throws away information. So if I add 2 disjoint sets, then it's pretty clear that the best estimator is simply going to add up the 2 independent estimates. And what that'll give me is this variance n squared over 2k. But if I look at just the usual MinCount sketch, then it always has a variance of roughly n squared over k. And so I get half the variance if I were just to add these things up. And this is equivalent to basically using twice the size. So the reason that this has performance which is twice as bad is that if I were to look at these sketches, so the red lines denote the thresholds, I'm essentially throwing away all of these points which are above the threshold on the bottom. So the threshold on the bottom is for the merge sketch. And so this is simply throwing away basically half of the information. The second inefficiency is that it's not using streaming estimates, which are optimal in the streaming case. And if we looked at the streaming estimates, they also have half the variance. And so basically you get this reduction from half the variance to 1/4 of the variance. The third inefficiency is that even if I were estimating the exact same set, then I can use the streaming estimates and average over them. And what this says is that when I'm taking these streaming estimates, there are different points which are actually triggering the increments in the streaming estimate. And so the ordering is actually providing some additional information. And so if I did this, then with MinCount, I can prove that the improvement goes from being twice as good to 3 times better. And for intersections, this problem is just not as well understood, so there are some other problems. So the most, I guess, a common way that people apply distinct counting sketches to do intersections is to apply the inclusion and exclusion principle. And there's this other estimate using a Jacquard similarity. And the problem with these sketches is that when I say do a union or just use these estimates directly, the large sketches error dominates. But in an intersection case, when I have unbalanced sets, I know that the smallest set is going to bound my error. So the error really should be proportional to the smaller sets, not the larger sets. So let's talk about the methods. The first method is the statistical method. It's basically applying statistical machinery to figure out what's optimal. Let's see how we're doing on time. Yeah. So in statistics, there's a principle called the likelihood principle, which is that all evidence related to the parameters useful for parameter estimation is contained in the likelihood. And so a very natural thing to do is derive the likelihood and perform maximum likelihood estimation. And what you can say with maximum likelihood estimation is that it's a asymptotically efficient estimator. That is, the variance of any other estimator is going to be larger or equal to the maximum likelihood estimator. And this gives you a very strong theoretical optimality result. So it's not a rate. The rate for all statistical estimation problems is basically 1 over square root of n, so no one cares about the rate. You only care about the constant. So in this particular case, the exact likelihood is intractable to compute. So we apply a method which is an approximation of this likelihood. So it's a pseudo likelihood. And we decompose it into 2 parts. One, which is a quadratic estimation, a quadratic approximation, which it takes into account the streaming estimates, and one part which is exact, which is just the hash values without the streaming estimates. And so like I said, if I can say that my quadratic approximation is close enough, essentially, to the true log likelihood, then I get the same optimality results. So I'm going to skip over the actual derivation of this likelihood, but it's essentially you can generate the thresholds, the hash values, and then which items are in the intersection. We're going to talk about the simple method, which is taking what I call component estimators and simply reweighting them optimally. So if I had 2 estimators for the union or 2 estimators for the intersection, then I can combine these 2 estimators by just taking a linear combination of them. And what you can find is that if I have a covariance estimate of this, then I was simply, the optimal weighting is going to be given by the inverse covariance matrix. And in particular, if we assume that that the 2 estimators are uncorrelated, then we have this very simple formula for it. So the main question is then, how do we come up with component estimators? So to get the best, in some sense, the best component estimators, we essentially want to find the 2 most uncorrelated estimators. Those would contain the most sort of mutual, the least mutual information, most independent information. And we can get this by looking at the very trivial inequality, which is just the intersection divided by the size of one set. You can translate this as being the Jacquard estimate, Jacquard similarity between the intersection and one set, Jacquard estimate similar with the other set, and multiply it times the streaming estimate. So in each case, the way we try to get the most uncorrelated estimates is that in each intersection estimator, we only use one of the streaming estimates. And the same thing happens for the union. So how do we get the Jacquard estimate? So remember in the slide where we talked about the merging inefficiency, the best Jacquard estimate we can get is essentially by looking at all of these hash values, which are less than or equal to the smaller threshold, so we don't throw anything away, and just looking at the proportion which are in the intersection. So how does this do? So if we were to apply these methods on just pairwise unions, what we see is that for the basic min count, so one is over here. One is I guess a likelihood-based method, and then we have red is the regular MinCount. The green is is if we didn't use any streaming estimates but sort of tried to do everything else right. And then our methods are at the very bottom. So we get basically MinCount is 4 times worse in the case where sets are disjoint as expected. We see that if we don't use the streaming estimates, then we do 2 times worse, which is equivalent to basically the gap between using streaming and non-streaming estimates in the non-distributed case. And for unbalanced sets, we have similar gains, but they're slightly attenuated. Oh, and both the approximately the sort of theoretically optimal, but not quite proved optimal method, pseudo-likelihood, and the sort of optimally reweighted component estimators basically perform the same. So you're not really losing anything there. Yeah. For our intersections, pairwise intersections, now you start to see really huge differences. So the naive exclusion estimator is much worse. In particular, if we look at, so the y-axis is how much more size you need to achieve the same accuracy, the factor. So that's important to note. In this case, when the intersection is very small, then you see that the naive inclusion-exclusion estimator does very badly, particularly in the case of unbalanced sets. So it's unbalanced in the sense that one set is 4 times the size of the other. The naive inclusion-exclusion estimator is 10 times worse in all cases. And so the bottom basically denotes the size of the intersection. What you also note is that if I were only to try to exploit streaming estimators, or I was only trying to exploit not throwing away too many hash values, in this unbalanced case, you see that there are both regions in which they do particularly poorly. And again, in this case, both the pseudo-likelihood and these reweighted estimators, they're by far the best. So now we can look at the case where we're taking many unions. So this is the distributed case, which the streaming estimators themselves couldn't handle. And what you see is that when the sets are closer to being disjoint, then you obviously do much, much better by factors. So this is with taking the union of 100 sketches. So in this particular case, it does 25 times better when each sketch only contained 10% of the union of all of them. You see that in this case, we also used random orderings. So this one, the previous two cases, elements are assumed to appear in the same order. We see that the gap increases from a factor of 2 times to a factor of 3 times when we exploit the streaming estimators. And in this particular case, we don't do the full covariance matrix and to compute the weighting, but we just make that assumption that things are uncorrelated. In this case, it does well. So in conclusion, so we proposed basically new methods for estimating cardinalities of unions and intersections. We show that they have good practical improvements, significant improvements in accuracy. They're easy to implement because they're simply these weighted linear combinations. And we sort of improved our understanding of these sketches. So we know that this pseudo-likelihood estimator is, if we can show that the approximation is good enough, which we conjecture it is, then it's equivalent to the optimal maximum likelihood estimator, and we identify why previous approaches to doing these problems introduced inefficiencies. Okay.
Any questions from the audience?
Hi, thanks, very interesting. So I think another fascinating area where this applies is this whole data privacy territory. And the idea is that you can share your data, but rather than sharing the data with somebody, you share the sketches. And all they can do is this computation. So I think if you look at some of the privacy papers, they try to look at the use of sketches as well. And what you're running against then is to try to think about these differential privacy guarantees, which essentially means if you do what you've done and then you perturb even a little bit your results, how far away are you getting from the bounds that you guarantee. So this is where I think this could also go as a research. Thank you.
That's interesting. Thanks.
Any other questions?
Yeah, I'm going to ask a question. So I'm wondering, this was interesting. I'm wondering what kinds of applications you're looking at for this, because it's interesting to see all the math, but then I'm wondering what kinds of things,
yeah.
if you can share.
So
Thanks.
I guess the so the applications, at least the ones that I'm probably most familiar with, are these online analytical processing applications. I think most of the sketching literature actually came out of networking applications from Bell Labs. But for these online analytical processing applications, you want to give, say, customers, whether they be I'm a little bit restricted in terms of like what I can say about particular business applications. But essentially, you want to provide real-time results about, say, who's seeing a web page, what type of people are seeing a web page or post, or doing some search queries, things like that. And you essentially just have tons of many posts. You have many search queries, which you want to provide analytics for.
Hi, I have one question. So we know that in the complicated SQL query or Hive query or Presto queries, so there could be a lot of conditions like join and group by or whatever. So will the algorithm lose their accuracy when you have very complicated join and group by? And the second question is that have you kind of implemented it in any Facebook internal system to test its performance, like on billions of users?
So I'll first answer the second one, which is that
Yeah.
I don't think I can really answer that question. But I do this work kind of out of interest, but it can certainly be applied in Facebook systems. For the first question, so this problem is trying to address the group by problem. So group bys, you don't really lose anything because they're just partitioning into many sketches, and we're trying to essentially kind of reduce the number of sketches that you might need. But in terms of joins,
Yes.
You can think of joins as basically being an intersection operation. So in this case, I'm not worrying about multiplicity of items, but you could probably add that in. But joins are just generally kind of difficult to do. So even in this case, right, intersection operations, I'm not going to get the same 1 over k type of variance result. So it's going to be something worse, which depends on the size of intersections, because hashes are essentially still random quantities. And when I take that independent random quantity, so when I take the join, I'm not going to have as much information available to compute those intersections.
I see. So can I ask one more question? Like how many times can you be faster than like Presto in kind of big data, like 1 billion lines of data?
Well, in terms of like scanning the data, right? This doesn't help you in terms of speed of scanning the data. And Presto implements hyperlog.
Okay.
So if you were to scan the data fully, all of the computation time is going to be basically in scanning, not in this computation part. But if you have these systems in which you've already aggregated things into sketches, and then you want to do further aggregations to answer some questions, then it goes from being a system which is like seconds, minutes latency to like milliseconds. So.
I see. Thank you.
One last question. Oh, go ahead. No, go ahead. Oh.
Sorry. It sounds like it's actually related to the previous question, but I'm wondering if your method generalizes to intersection of multiple sets at the same time as opposed to just pairwise intersection.
So with MinCount, it's easy because I can compose the sketches. So I can, after I get an intersection, I get basically another sketch, and I can do that again.
Right.
If you were
Do you
to
lose
think about
anything in
things which
doing
are,
it sequentially as opposed to
yeah,
doing it all at once?
You could. I think, right, the estimators you can also just generalize. You just take all of the hash values less than the smallest threshold, count the proportion which are in the intersection, and multiply it times each particular streaming estimate. So in that sense, you can generalize that reweighted estimator very easily to multiple intersections. I'm not sure. I think if you take multiple intersections, your performance degrades potentially pretty quickly. For other sketches, right, the simple reweighted estimator they could be pretty easily generalized to say hyperlog log. But in that case, you wouldn't be able to do this sort of. It's much more difficult to. Well, you can't do this. You won't get another sketch out if you do an intersection. And if you did multiple intersections, I think you could do it in this very similar fashion, but it might just be a little bit more tricky.
Last question.
All right, thank you. Is getting the exact cardinality of your interest, and why or why not?
Scaling the computation of the exact cardinality, is it of interest?
Rather than the approximation.
So I mean, it's always of interest, but I don't know if you can. But you have these sort of fundamental size and speed problems, and so I don't like if you have to scan a terabyte of data, you have to scan a terabyte of data, and you just can't get past that fundamental speed.
Yeah. So for instance, if you get a very large amount of data, but however the exact cardinality is relatively small, to me it's still of interest to get exact count rather than approximation.
Yeah. So all of these methods, the error scales as roughly as the size divided by square root of the number of basically samples that you're keeping. But so in the case where you have a very, very small count, say for MinCount, if your sketch size was 100 and you had less than 100 items to count, then your result would actually be exact because you actually stored you would be storing a hash table of all of the results. So,
But provided you don't consider the collision, right?
yes, yeah. So if you don't, so the collision problem is not really a big deal if you have a small count and like 32 bits. So, yeah.
All right, thank you.
Thanks again.
Thanks.